that. Let's see. Yeah, the color looks good. Okay, cool. All right. So, what we're going to talk about today is the conservation of energy. Now, yesterday we kind of briefly touched on what energy was, what work was. So, what I want to briefly go over again is the difference between. Of course, I chose the wrong one. No, there it is. Okay. So, I pause it and I put the person up here. So notice that the total amount of energy that I've got in the system, there we are, is going to remain the same while the person is moving. All right, so friction is off. Stick to the track. Put the speed up there. All right, so when I hit play, what I want you guys to see, so the reference height, yeah, okay. So the total amount of energy will not change. But when I hit play, you'll notice that the amount of potential energy, in this case it's gravitational potential, will be converted into kinetic energy, which is the energy of motion, as the skateboarder goes down the ramp and then back up. So I'm going to play that. And notice when they're at the maximum height, that's where the maximum potential energy is going to be. When they're at the very bottom, that's where they're going to be going the fastest. And because that's going to be the maximum velocity, that's where the maximum kinetic energy is going to be. And you'll notice that once they get down to the bottom, well, if I did it correctly, wish there was a way I could step it through. Come on down. Yeah. So it's not perfect, but you can see here that the potential energy is almost zero. Hold on. How does he balance? Well, we don't know the gender, first off, and it's a 2D animation, so I think their balance should be pretty good. But down here, the reference height is right here at 0. And the potential energy is dependent on how high, or the displacement from the reference height. So in this case, it's on the ground. And the red dot is on the ground. So in this case, the reference height would be 0. And where they're the maximum distance away would be at the top. So that's where they would obviously have the most potential energy. Make sense? Well, gravitational potential energy. Now, there's another type of potential energy that we're going to mention today. That's going to be elastic potential. So that's going to be dealing with springs, elastic bands, anything that has like a restorative property. But in this situation, what I was demonstrating was that the total amount of energy remains the same. And I want to point out that if you take this green bar and I put it on top of the blue bar, no matter where the person's at, if I do kinetic plus potential, it's always going to equal my total. Okay. So that's the conservation of energy. So my starting point is going to be right here. So that would be state 1, or my initial state. And then if I wanted to figure out what my velocity would be down here, this would be my final state, or state 2. So when we're comparing, or when we're discussing conservation of energy, we're going to be referencing a scenario, but there are particular states that we're going to have to declare, if that makes any sense. So my initial state, my final state, and then if it's continuing on to do something different, then my initial and final state for the next part would possibly be different. Okay. So on the assessment for this material, there's going to be a situation where there is a box that's on a ramp, very similar to this. But then when it comes down, it's going to come down and it's going to slide across the ground, and then it's going to hit a spring and it's going to compress the spring. So there's going to be 3 different states that you're going to have to take into account. But the way that I designed it is that for each of the states, there's only going to be one type of energy present at each state. Okay. So what I want to do now is go over what the conservation of energy is, the 3 types of energy that we're going to be using, and what those types of energy equations are. So the conservation of energy is simply this: the total amount of energy at state 1 must equal the total amount of energy at state 2. As simple as that. Energy that I start with must equal the amount of energy that I end up with. That's all it is. So there are 3 types of energy that we're going to be referring to. So kinetic energy is, of course, energy of motion. You have gravitational, potential energy, and that's the energy I'm going to write today. Apologize. So this is the energy that, like, if you increase the amount of distance from the surface of the Earth or some reference point, like we've got here. So if I have the person at the very top, my reference point is down here. But if my reference point is here, the distance between this reference line and that red dot has decreased. So as I increase the distance between the red dot and the blue line, notice how my potential energy goes up. And when we do problems, the reference line is always going to be the ground, the surface. Okay. And then lastly, we're going to have elastic potential energy. Now, I want to put spring in quotes because it's not necessarily always going to be a spring. But in the examples that I'm going to be using, we're going to be using springs. Cool. So just to have a quick recap, kinetic energy is the energy of motion. So if an object is on Earth, obviously it has to have mass to be considered an object. So mass has something to do with it. And because it's energy of motion, it has to have a velocity. So if there is no velocity, there is no kinetic energy. Gravitational potential energy, that's the energy stored by creating a distance from the surface of the Earth or from a particular reference point. So the higher up you go, the more energy you have stored. And then when you start falling towards the earth, that's going to be converted into kinetic energy. Elastic energy is something that is energy stored by a spring. So if I compress a spring and I let it go, it's going to release that energy. Or if I pull a spring and I let it go, it's going to release it and go in the opposite direction. Cool. All right. So those are the basic definitions. And what we're going to do is we're going to talk about what the total amount of energy is composed of. So all it is just I add up all of these types of energy together. So my kinetic plus my gravitational plus my elastic. That's all it is. And that's going to be at my initial state and my final state. So what does that look like? So my total amount of energy for a particular state is going to be equal to my kinetic energy. So what I try to do to represent the energies, I usually do that on the whiteboard. So it's a little bit messy here. So I do a capital K with like the little lines on like the legs of it to represent kinetic energy. And then that's going to be added to, there's going to be a capital U, and then I'm going to have grav for gravitational potential energy. And that's just a common notation. I'm not 100% sure why they use the letter U, but physics. And then we're going to have U elastic. So like I mentioned yesterday, there are multiple types of potential energy. So we have gravitational, elastic, chemical, electromagnetic potential. But in this course, we're only going to be talking about gravitational and elastic. Okay. Any questions so far? Okay. So this is the total energy of the system. This is kinetic energy. Gravitational potential, and then elastic potential. Okay. Now, where it gets a little messy. So there are some questions that, well, how about I give you guys the equations first, and then I'll give you guys a quick housekeeping tip. So these equations I would highly recommend you write down in the formula sheet. So the equation for kinetic energy is going to be equal to 1/2 times the mass times the velocity of that object squared. Mass, velocity, and you already know what kinetic energy is. So if I increase my velocity, what happens to my kinetic energy? It goes up because it's a direct relationship. If I increase my mass and I keep my velocity the same, my kinetic energy also goes up. So if you think about it, if I had, say, a dump truck and then a smart car, and they both had the same velocity, v, which one has more kinetic energy? Would it be the dump truck or would it be the smart car? It would be the dump truck because it has more mass, right? More mass, more kinetic energy. Okay. All right, let me get Kumon. Oops. Give me 1 second, guys. I apologize. All right, hold on. I need to retake attendance real quick. Did Wendy show up? Wendy's here. Trevor's here. Sean's here. Nathaniel's here. Talia, Natalie. Natalie's not. Kimon just came in. Isaiah is here. Isaiah's not. I think everybody else was here. Okay. All right, I apologize. Okay. So the next one would be gravitational potential. So this could be capital U, grav. And this one's probably the easiest. So it's just going to be mass times the acceleration due to gravity times the height from the ground. Okay. And real quick, we're going to have kilograms. We have meters over seconds. You have kilograms, meters over seconds squared, and then this one is meters. I know it's a little messy, but hopefully you guys are tracking what I'm doing. Okay. Any questions so far? All right. And then lastly, this one is where it gets a little strange. There's a concept in here that is pretty easy to understand if you pay attention. So U elastic is just going to be 1/2 times the spring constant times my change in position from it. So the amount of compression or stretching of the spring from its rest length squared. Okay, so what do I mean by that? So let me write this down real quick. And then So when we have a spring, there are different types of springs. Like there's different strengths of springs. You can have a very springy spring, or you can have a very stiff spring. And in order to attribute a value to how stiff or how springy a spring is, that's what this spring constant is. The spring constant has units of newtons over meter. So what this represents, and of course, delta x is going to be in units of meters. So if I have a spring, yes, Sean? Oh, yeah, no, I got you. Okay, so if I have a spring like this, and I have a distance, so if I have a spring that's just sitting there, the without applying a force, the length of that spring, the physical measured length of the spring, is called the rest length. And hopefully the green will show up. So this will have a length like this. Cool. Now, if I stretch this spring, copy, paste. This has a new length like this. And the difference between the two, so this length here, or I'll call this delta x. How about that? That would be the delta x. Does that make sense? Is there any confusion about that? So if I stretch a spring, or if I compress a spring, depending on how the spring is made, it can be made for compression or for decompression, stretching or compression. It all depends on the type of spring. So what the spring constant represents, this newtons over meter, what this means is how much force is required to stretch a particular spring 1 meter. Okay, that's all it means. So if I have a stiff spring, I'm going to have a higher spring constant. And the spring constant is the variable lowercase k. And what I usually do is I do like a little hump like that, instead of like the normal k like that. It's kind of hard to do it on the screen like this. On the whiteboard, it's a lot more prominent. All right. And loose spring. Low spring constant. So since there are two types of Ks that we're using, I mean, these are the same, but what I'm referring to is this and then the variable for kinetic energy. That's why with kinetic energy, I put the little bars on top to make it more explicit. Cool. All right. So the spring constant is the amount of force required to stretch or compress a spring a distance of 1 meter. So that's all the spring constant is. Oh, there's Natalie. Okay. Any questions so far? So we're almost done. And when it comes to the video on YouTube, I have found out a way to put what they call chapters, so you guys can skip through the video and you know like when I talk about a certain topic, so you don't have to like scrub through it and try to find it. And once it's uploaded, I'm gonna put the definition of spring constant, like diagram of spring constant or displacement from rest length and all that kind of stuff. Let me put this in here. So that's the rest length. Okay. All right. So the last thing I'm going to talk about is when we look at this equation, this total energy equation, when we're solving problems, you can probably look at this and recognize that this will get very messy really quick. If I do E total for the starting position, like in situation 1, so if I go back over here, so my initial position would be E total, so my total amount of energy, so this part right here is going to be equal to my kinetic energy plus my gravitational potential plus my elastic potential, right? So when I start, I'm going to have to take all 3 of those into account. Now, if you do it in a very mathematical way, you would take all 3 of these variables, all 3 of the types of energy, and then you would plug in what each of those energies are, and then you would cancel things out. Okay. So right off the bat, that's not how you do it. Technically it is, but I'm going to show you a much, much easier way. So we can immediately cancel out 60% of this, or 66.666%. We only need a third of that information. So there are 3 different questions that you can ask yourself at each different state when we're solving these problems. And that'll help you potentially cross out 2 of the energies. So any of the problems that I give you, there's only going to be one type of energy present. It's either going to be kinetic, gravitational, or elastic. Okay. So, out of curiosity, what type of energy is present at this state? Anybody tell me? So the very first question that you ask, is the object moving at this state? So obviously the simulation is paused, but what I can do is I can look at the speed of the object. Do I have a speed or a velocity? If the answer is yes, then I have kinetic energy present. If the answer is no, then I do not have kinetic energy present. So I don't have to write the kinetic energy part down. So let me show you what I mean by this. So what I'm going to do is I'm going to, instead of waste time in writing this over and over and over again, copy that. Bear with me. Oops. Okay, so this would be E total 1 equals E total 2. Okay, so this is the total amount of energy at my initial state. This is the total amount of energy at my final state. Now, how I'm going to notate this is my kinetic energy at state 1, my gravitational potential energy at state 1, my elastic at state 1. State 2, state 2, and state 2. Okay, so obviously this looks a little intimidating, right? But here's the scenario. What I want, like, we're not actually going to do a problem, but this is kind of a way to explain how we can simplify our lives. So at this state, is the person moving? At state, so this is going to be state 1, and then when they reach down to the bottom, that's going to be state 2. All right, so that's what we're going to be doing in this example. So state 1, they're at the maximum height. My velocity is 0. So therefore, if my velocity is 0, my kinetic energy is 0. So what I can do is I can go ahead and I can cross out kinetic energy at state 1. Make sense? The second question, and I'm going to write these questions down after I go through this example. The second question is, does my object have a height from the ground? Is there a distance from the ground to my object? So at state 1, is there a distance from this line, this blue line, to the red dot? In this case, the answer is yes. So I do have gravitational potential present. So I'm going to put a box around gravitational. So that is present. We do have that there. And lastly, the third question is there a spring that's either being compressed or stretched at state 1? And when I say compressed or stretched, that's due to the object that we're referring to. So is there a spring even present in either one of these states? The answer is no. So there is. All right, you're fine, Alex. So since there is no spring even present in this scenario, then obviously there's not going to be any elastic potential present. So then we can immediately knock out U elastic. Is everybody tracking so far? So currently, the only energy that is present at state 1 is just going to be U grav, which is gravitational potential energy. Yeah, go ahead, Malik. Okay. So the only energy that's present is going to be gravitational potential at state 1. So instead of having the equation for kinetic and the equation for elastic all written out, all substituted in, this is going to make our lives a lot easier. Now, at state 2, like I mentioned before, this is going to be the point where the skateboarder is at the very bottom. So the very first question I have is, does my object have a velocity? I look at my speed at my state 2. Is there a value here? Sure enough, we do have a velocity. So if we have a velocity, that means that we have kinetic energy. Kinetic energy is the energy of motion. So this is present. Is there a distance from the ground to my object? The ground in this case is this dotted or dashed blue line. The object is referring to the red dot. That's our point of reference. Is there a distance between the two of those? In this case, the answer is no. So we do not have gravitational potential. So gravitational potential goes away. And then, like we mentioned before, there is no spring that's either being compressed or stretched by the object at the state because there's no spring present. So we can go ahead and cross out elastic energy. So at state 2, the only energy that is present is kinetic energy. So all of my energy at state 1 was in the form of gravitational potential, and all of my energy changed from gravitational potential into kinetic when it got to state 2. And I know that the total amount of energy remains the same throughout the entire process. So my total amount of energy remains the same. So it doesn't matter where I'm at, all of it stays constant. The total does. So if all of my energy that's present at state 1 is potential, and of course it didn't go all the way back down, but and all of it is kinetic, then I know that both values, like if I plugged in the values that I had for mass, velocity, and height, I should get the same numerical value for gravitational potential and kinetic energy at both states. I should get the same number on both sides. Now, when I give you guys problems like this, actually, let me substitute what these actually mean. So mass times gravity times the height from the ground. And it's a little too far over to the right. And then I got 1/2 mv squared. So when I give you guys a problem, I will give you all but one of these variables. Okay. So I may ask you, what is the maximum height if the velocity at state 2 was this? Like, I would give you a number for that. And remember that the acceleration due to gravity in my class is going to be 10 meters over seconds squared, just to make the math easier. So I would either give you the velocity or I would give you the height, and I would ask you to solve for the other one. Now, does the mass have any effect on how high I go or how fast the object is moving? If I increase or decrease the mass, does that have any bearing on how high the object will go or how fast it will go? Let's see. So if I move my person up here, and let's see. All right. So the maximum, so it's 10.7, 10.8. So 10.8 was the maximum. Okay. So if I increase the mass, let's see what happens. So what did I do? The total amount of energy increased. So let's go back up here. So as I increase the mass, the total amount of energy increases. So I have a greater potential energy. So when I hit play, oops, put on slow real quick. Pause right there. And would you look at that? The maximum is still 10.8. But notice that my total energy goes up, but because both gravitational potential and my kinetic have mass in their equations, so since there's mass here and mass there, whatever I do to mass, whether it be increasing or decreasing, it's going to affect both sides the same way. So it doesn't affect the rest of the other variables. So in other words, mass does not matter. Now, in this situation, because it's an ideal situation where there's no friction, mass doesn't matter. If friction was present, like it would be in the real world, that would affect the normal force, which would thusly affect the force due to friction, and that would make a difference. But in an ideal situation where there's no friction present, mass does not count. Like mass doesn't matter. So I can have 5 kilograms, and I'm going to try to keep consistent. All right, so So it's still 10.8, and I'm only at 5 kilograms. But then when I boost it up to 100, try to keep it the same, I'm still going to have the same value for my velocity. Does that make sense? Okay. So I'm going to, I think that covers everything that I wanted to cover today. So I'm going to go ahead and end the live stream, and I'm going to show you guys a video of some video evidence of why mass doesn't matter, or I'm going to prove to you that mass doesn't matter with the video dealing with a bowling ball and feathers